All right, our last lecture of this unit on chemical reactions is on bond enthalpies. And bond enthalpies is a table on it determines the amount of energy. All right, it's the amount of energy in order to break. Okay, 1 mole. We're going to talk about the mole, that's our next unit. 1 mole stands for 6.02 times 10 to the 23rd number. Just like a dozen stands for 12, a mole stands for 6.02 times 10 to the 23rd. So it's the amount of energy needed to break that many bonds of that specific type of covalent bond. So all of these energies here, you can see right here, a single bond for carbon to hydrogen. To break 1 mole of those bonds, 6.02 to the 23rd of them, would require 413 kilojoules of energy per mole of CH single bonds. So the higher the bond enthalpy, or sometimes called bond energy, the higher the bond energy, that tells us the stronger the bond. If it takes more energy to break it, a mole of it, it is a stronger bond that is formed. It takes more energy to break it. All right. So bond enthalpy tables is always got positive values because breaking bonds is an endothermic process, which means it takes energy. Okay. So to break bonds is an endothermic process, which means energy is going in. All right. Okay, I'm going to kind of review a little bit from the last topic real quick before we go through the example problems. So when we do these problems, you've got to figure out how many bonds we have to break and how many bonds we have to make. The breaking is an in, the making is an out, and the difference in those two will give us the enthalpy of the reaction. So in order to do that, you've got to figure out how many bonds are going to be broken and of how many. All right? So the first step to do these problems is you have to draw the Lewis structure. So real quickly, if you want to pause the lecture right now, draw the Lewis structure for each of the chemical compounds in this reaction. All right? So pause the lecture now and do that. For those that are coming back, CH4 should be drawn like this. Oxygen should have a double bond between it. Okay. Carbon dioxide's got a double bond between each carbon. And water has got a single bond. Now, one other thing that we have to take into account is the stoichiometry. There's a 2 in front of both the water and oxygen. So that means we need 2 molecules of oxygen being present and 2 waters. Now, you either can draw them like I did, or you can just say off to the side times 2 or something like that, just so you know you've got that. You have to make sure to account for all of the bonds. Okay? So on this side, we have 4 carbon-hydrogen single bonds. And because there are 2 molecules, we have 2 oxygen-oxygen double bonds. We're going to subtract from that 2 carbon-oxygen double bonds because there is a bond on each side. So there's a total of 2 carbon-oxygen double bonds. And because, again, there's 2 molecules, there are 4 OH single bonds. We're going to sum up all the bonds that we have to break and all the bonds that we got to make, and then simply do the math. So the hard work is actually done for us already. So 4, we go up top, and the carbon-hydrogen bond, as I said, is 413, plus oxygen-oxygen single bond. Actually, for this one, they tell us that an oxygen molecule is 495, but there's 2 of them. Because if an oxygen forms a double bond with itself, that's all you're going to form is O2 molecule. All right, so we're going to add that up, and we're going to subtract then 2 times the carbon-oxygen single bond, a double bond, which is 799, plus 4 times OH, which is 463. Now, one thing I do want to make a mention to this, and if you want to punch in this calculator as you're listening here, a carbon-oxygen single bond has got a value of 358. A carbon-oxygen double bond, has an energy of 799. You'll notice here, based on the numbers, what I can do is if I've got a double bond between carbon, I just simply cannot take the carbon-oxygen single bond and times it by 2. It does not work that way. You have to look up the specific type of bond that is present and then apply how many of each you are either breaking or making. So don't just double the single bond in the double bond. It doesn't work that way. So if it's a single bond, look up the single bonds. If it's a double or triple bond, look up the multiple bonds and break the according bonds and do the appropriate math. All right, so 4 times 413 plus 2 times 495, we get 2,642 kilojoules in. This is the amount of energy we have to break. That's how much it takes to break the methane and the oxygen. And we're going to subtract now 2 times 799 plus 4 times 463. We get 3,450 out. Therefore, when we subtract now 2,642 minus 3,450, we get negative 808 kilojoules. This is the enthalpy of the reaction. The value is negative, and if you have negative enthalpy, that means it's an exothermic relationship. Okay, it's exothermic. And this is an example of a combustion reaction. All combustion reactions are exothermic. They give off energy. And the reason they give off energy, and they tend to be quite large exothermic. All right, I'd like you to pause the lecture right now, and I'd like you to go ahead and do the same process for number 2. Draw the Lewis structures, figure out how many bonds you got to break, make sure you apply the appropriate number of molecules based on the balanced equation, and see if you can get the right answer. Next time you start the lecture up again, you're going to see all my work provided already, and hopefully your answer will match mine. Make sure you do the problem now. Pause the lecture now. All right, NH3 has got 3 single bonds between nitrogen and hydrogen, again following the octet rule. Nitrogen forms a triple bond. Some students tend to get this wrong. It's a triple bond, and then hydrogen single bond. So again, because there's a 2 out in front of the NH3, there's not 3 NH bonds, but there's a total of 6. We would have technically 2 molecules of NH3, which would be a total of 6 NH bonds. 1 triple bond between nitrogen and 3 single bonds, again, because there's 3 molecules of hydrogen, a single bond in each. So going ahead and doing the math, you can now see 2,346 energies in to break all the bonds and 2,249 kilojoules out to make the bonds. Therefore, more energy goes in than comes out, and therefore we get a positive enthalpy, which means this is an endothermic process. So in order for this reaction to sustain itself, energy has to keep going in and into the reaction, and therefore we have to either put energy into it in any type of form. We might have to hook it up to a battery, we might have to heat it, we might have to supply the energy in order for the reaction to occur, because it continually consumes energy in order to make the products, which are in essence not as stable as the reactants are. Okay, let's turn to the last lecture. We talked about energy diagrams. In an energy diagram, the reaction starts off with the energy content of the reactants. Then it goes up. It always goes up first, and this is called the activation energy. EA is called activation energy. This is the amount of energy that the collision between the 2 particles has to be in order for it to get over the hump and form products. If the collision doesn't meet this requirement of energy, it is an unsuccessful collision and no products can form. Okay? Well, really the activation energy really is the energy in. It really stands for the amount of energy to break the bonds. So we now have a table that we can look up these bonds and we can figure out how much energy is coming in. So the activation energy is the energy in. And at the very peak of that hump is called the activated complex. The activated complex is just a theoretical concept of a structure that has both the reactants and products all together as one big, large macroscale molecule, and it can either break apart back into reactants or it can form products. Okay? But if I look on the other side of this line from the hump, this is the energy that is out. This is the energy in. So the amount of energy in we can compare to the out, and the difference in those energies will be the enthalpy of the reaction. So if I'm looking at bond enthalpies or bond energies, all I've got to do is take the energy in and subtract from the energy out, and that'll give us the enthalpy of the reaction. Delta H is enthalpy, which is the amount of energy that either goes in or out of the reaction in order for the reaction to form products. Okay? So if more energy goes in than comes out, then the products would be above the reactants, and a surplus of energy has to keep coming into the reaction for it to be sustained. Vice versa, in this example here, this is an example of an exothermic graph because we're going to get a negative enthalpy whenever the products are below the reactants is exothermic, and therefore there's more energy that comes out than goes in, and therefore there's a surplus of energy, and that surplus of energy is going to go or be liberated out to the surroundings. And if energy goes out to the surroundings, it makes the surroundings feel warmer, i.e. a hand warmer. So because there's an excess of energy coming out, that's why it will warm the surroundings, because there's a net amount of energy that has to be expelled in order for the law of conservation of energy to hold true. Okay? So is because the products have less energy than the reactants. So when the products form, they release more energy than goes in, and therefore there's a surplus of energy, and that energy in the combustion can be used to fuel your cars, it can be used to heat your homes, it can be used for a lot of different purposes. But combustion reactions tend to be exothermic. Okay, so there's one last problem to do here in the packet, and this is this one here. Again, I'd like you to go ahead, pause the lecture, draw the molecules, their Lewis structures, and make sure to apply, again, the coefficients appropriately. And then when you restart the lecture, let's see if you can get this one right. All right. You can now see my work here. Again, the C2H2, there should be a triple bond between the carbons in order for, again, the molecules to follow the octet rule. I will not have any reactions in this unit which do not follow the octet rule. Obviously, unlike hydrogen, again, hydrogen never gets to 8 anyway because it only needs 2 electrons to fill its orbitals. But all the molecules other than hydrogen will follow the octet rule. So again, make sure you're following that rule and having 8 electrons on each central atom. Other than that, to break this, we have 2 carbon-hydrogen single bonds and a triple bond between the carbons. There are 2 molecules of H2, so there are 2 HH single bonds. And then we add it all up for a total of 2,537 kilojoules of energy in to break all those bonds. We make the molecule ethane in return. There are 6 carbon-hydrogen single bonds, and students often forget this one bond in the middle. Not sure why, but they tend to forget about that one. But there's also a carbon-carbon single bond, which is 348, for a total of 2,826 kilojoules out. Subtracting, we get a total, again, energy in versus energy out. We get a total of negative 289. So this again is the enthalpy of the reaction, and because the enthalpy is negative, we know that this is an exothermic reaction. All right, that's how we can calculate the enthalpy of a reaction, the amount of heat that either comes in or out of a chemical equation. Why? The law of conservation of energy. If there's not as much energy that goes in as out, therefore energy has to be expelled out to the surroundings because of the fact of the difference in energy. If it's the other way around, then energy has to come in, and that has to be supplied by people or some other part, maybe the sun, maybe electricity, plugging something in, maybe heating it up, combusting something to cause the energy. But in other words, energy has to come in to support the reaction. So energy really dictates if a chemical reaction will occur or will not occur. All right. So this week with the homework, there's a homework sheet. Those of you that are going to be in class, I would like you to not this week to not do the homework problems, because I'm going to utilize class time this week in order for you to go ahead and do those problems. Those of you that are not going to meet this week, which would be cohorts B and D, please do the homework assignment that's in Canvas. If you have any questions, please reach out to me. I'll be glad to set up a meeting or just answer your questions through Canvas or an email. But otherwise, work on these energy problem diagrams and also work on these bond enthalpy problems and utilizing that. Next week, we'll review early on and we'll take the test on chemical reactions next week. Again, as always, thanks for listening.